So just call me Jerry. And so today I'm going to introduce some microscopy principles and also our size products. So I would like to ask if there are any microscope users here. Anyone use light microscope? So all you have experience with microscope, right? Okay. So let's move on. Oh. Okay. So here's our agenda today. So we have 6 sections because we have only like less than 1 hour. So I will talk a bit quick. So here's our main applications about microscope in academic or industry fields. So you can see on your right-hand side, so here's a typical cell image taken by confocal microscopes. And beside biology and also maybe some agriculture fields. Here you can see on your left side, mainly in Taiwan, our customers are from industry. So you can see here, like we can examine like a wafer or some steel products to examine the surface or any production failures to see the features. But today here we mainly focus on biological samples. Then anyone knows the companies in this slide? So maybe everybody knows the TSMC, right? Because this is the most famous Taiwanese companies in the world. And besides, during the pandemic times, we also faced the like COVID virus. So for Pfizer, AZ, so they also use microscopes to do the biological experiments. And besides, there's also like academic silicas, and for the industries like the airline, EVA Air, and also the Mitsubishi, the Japanese company, which is famous for producing cars and also elevators. And also, you know, the German companies like BMW. So for size, actually, we have like mainly 3 product lines. The first one is the most common, light microscopes. So here you can see from the stereo microscopes, wide field microscope, and confocal microscope. Also for the super resolution microscope. So these 4 microscopes are the most common products or machines in the world. Further, it's like 8 years before, Zeiss actually invests a lot of budgets in X-ray microscopes, because by using X-ray, we can examine the samples without dissection or to destruct our samples. We can just use the X-ray light, X-ray to transmit the samples and gain the 3D image data set. And also for the electron microscope. Zeiss used to have transmission electron microscope, but for now we just focus on scanning electron microscopes. So here you can see like the common scanning electron microscopes, and to the more advanced like the focused ion beam, SEM, and also for the helium ion beam. So here's some typical products for light microscopes. And from your right-hand side, maybe you already know the name, the most typical actual imager and the LSM 980s. So maybe you already use this one in this institute, and also with Eriscan modules. For automatic microscopic, here we have the actual scan. This is the actually called slide scanner. So you can like have HE scan or lots of fluorescence samples which made into slides. Then we can scan these 4 slides like 100 or 1000 slides daily. Then we have other systems which is mainly in the inverted microscope. So here's the observer is a inverted type microscope and with fluorescence functions. And for the most advanced modules is called Lyra 7 and with the latest steam square functions. Then maybe you already know these 3 major types of microscopes because we use upright microscope to observe the slide samples, and for the inverted type, we mainly observe like live cells or other specimens immersed in the solution or buffer. And before any experiment, you may also need stereo microscope to do some dissection or to examine your samples, like zebrafish, or maybe you have plant samples. So basically, sample size determines which type of microscope we would like to use. And here we can see the diagram, some visualizations. If we want to image like slide samples, we prefer to use the upright microscope because we can have the most clear, high-resolution images. And we have live cell or floating type samples, we may want to use the inverted microscope. Otherwise, we cannot just turn our petri dish upside down. And for very large samples, even like a pineapple, we would want to use the stereo microscope to examine from the leaves on the top and to the bottom with some peels. And maybe in like 10 years, automations of microscope is the main trend. So like molecular device and some like agent. You may heard some other companies, they invest their monies in making automatic microscopes. So there's no IPs on this type of microscopes. You only see you can put your samples into these kind of machines, very user-friendly, and just one click, then you can do the complete workflow imaging, like this automatic slide scanner, and this one is called Cell Discover 7. This is the automated inverted microscope. You can imagine we can cover the whole LSM 980 into this one. And this is the history. So in the very beginnings of the 19th centuries, people may have some plagues and they really don't know what caused this kind of syndrome. And here's Carl Zeiss produced the first standardized microscopes to view the specimens efficiently. Because without standardized microscopes, during the time in 19th centuries, doctors or other physicians, they cannot understand what is the syndrome. You can see under the bright field microscope, and the arrow points the bacteria, which cause tuberculosis. And so Robert Koch actually thanks Carl Zeiss for providing the excellent light microscope, so he can solve the problems. And here we can see this the antique type of light microscope. And in the middle of the slide, we can see actually light microscope is composed with like mainly three parts. From the objective lens. In the middle is the stage, which can hold our samples. And in the bottom is the transmitted light source. In the past, we usually use the like sunlight or the candle to reflect the light to the stage and to the samples on the top, then to the lens, objective lens. And here we can see the animations. Then nowadays, actually, we just change a little. You can see we have some fancy stuff like digital cameras, which is made with CCD or the CMOS chip. Or this is the automatic stage. So you can do like the position settings and do the automatic workflows. Also, we have the fluorescence filter set. You can choose to image your label samples with like Data channel or Alexa. And for the upright microscope, the main benefit is the high bright field resolution. So if you want to image the HE stain or the depth, or maybe dark field, upright microscopes is your best choice. However, we have some problems because upright microscope have very short working distance, which means from your samples to the objective lens, the distance in between is very short. And it is actually shorter than the height of the common plastic petri dish. So actually, we cannot put the petri dish in between the objective lens and the stage. Sometimes we may try to use the DP lens to do this kind of work, but there's also some practical limitations. Here you can see this doesn't work. We cannot just put the petri dish under the objective lens, because the most common objective lens, they cannot be placed in the buffer, otherwise they may be lost, or the lens will be like not transparent anymore. Also, if we image our cells, which are cultured in the buffer or the medium, and if we try to observe the cells from the top side, and we just assume this is the beautiful cells, right? And we will want to observe these cells from the top, but actually, if we see from the downside, it's like unexpected. This may not be the cells we want to observe. So this is actually the guy in the water. So thanks for the John Lawrence, and he invented the inverted microscope. Here you can see the petri dish. A petri dish can be placed safely on the stage, and the objective lens is placed underneath the stage. So there's no limitations caused by the working distance of the objective lens. Here, the only thing we change is the location of the transmitted light source and the objective lens. We still put the samples on the stage, and we can see there's some benefits for the inverted microscope. We can do the live cell images, because we can just put our petri dish or our flask, you can see flask or multi-wells, any kinds of containers, just put it on the stage. And because we have longer working distance for our condenser lens, you can see here, this one is our condenser lens. So for the longer working distance, we can put samples with much higher height. We just mentioned the flex type of sample carrier. And this kind of design for the inverted microscope actually have some it's like disadvantage. We call it is we have a much lesser numerical apertures for the condenser lens, which is the maximum value is around 0.55. And so if you want to do the like IHC images, I would advise you to take the images by using the upright microscopes. And here you can see this is the typical set of the confocal microscope systems. And we can do very dedicated, high-resolution live cell images. This is the DIC images overlaid with the fluorescence labeled channels. You can see the nucleus and also the mitochondria. And besides, inverted microscope also have some benefits. If you want to do the IVF, in vitro fertilizations, because for this kind of applications, we want to apply other like the machine arms to do some fine books, I would say. So the one on the left side is the thicker needles, which can suck the eggs from the human bodies. And this one, the tiny needles on the right-hand side is for injections. So maybe we can we inject the sperms into the eggs. So sperms comes from these tiny needles and penetrate through the outer layers of the egg. Then go inside to do the fertilizations of egg. So you can see we can only do this kind of works by using the inverted microscope. And if we have really big, large samples like the pineapples, or maybe we need to do the mouse dissections, or we have like mineralogy and just such kind of stuff, we can use the stereo type microscope to do the observations. So here, this one is the more typical type, and the fancier one is with much more automations. So stereo microscope actually provides the 3D visions, which means you can clearly understand the difference between the objects which is close to you and also the objects which is far from you. This cannot be done by using the upright or the inverted microscopes. You cannot understand which layer is near you and which layer is far behind. And besides, the longer working distance can provide you the convenience to place the samples in between, so you can see any kinds of literally any kind of samples. And also, we have much more space like here. So this means we can actually put any kinds of illumination source, maybe from maybe just nearby, or like a typical set. Here we can have light here from the side, and also light from the downside. So we just mentioned we can use these kind of stereo microscopes to observe the plant samples, maybe like you want to do the wood sections, or to observe the zebrafish, sorry, and some other much more big samples also for like Drosophila. Because for this kind of experiment, they usually do some pre-treatment before they do the further high resolution imaging. Here, we can see the illumination is actually very versatile. This is the gooseneck light, so you can adjust the angle of the illumination very freely. Also, this is the fixed type, so you only do the surrounding illuminations. Besides, from the illumination from the top, you can also adjust the illumination underneath. So here you can see we can actually have like 5 types of different illumination to observe the transparent samples. You can see there are different effects. You want to emphasize the transparency, or you want to emphasize the curvature of your sample. Okay, let's keep going. So now we need to go into some theories aspect. So why do we need to use microscope? We all know the reason. We want to to zoom in to see the tiny samples more clearly. But actually, there's limitations about the magnifications. So no matter how expensive microscope you use, you have the same limitation is around 1,500x. And so how is the limitation of the magnification? So let's see this kind of image. Here we claim this image is the 8K image. We assume it is Ultra HD image, but you know this is not. So even we zoom in and to look the image more closely, we still don't know what does it means, right? Because we know it is ultra, but we just cannot see the letters clearly. So that's why we need to focus on resolutions. Magnification is an issue, but the determined issue is caused by the resolutions. So that's why we emphasize on we need to have high resolution image. We just compare the image on the left and the one on the right. You can see even we take like using microscope to take the tiny data set like here, then we transfer our data to our laptop or PC, then we enlarge the data. The image with high resolution can actually provide the good magnifications for your research. For the definition of resolution, here we can see that here it says that the resolution limit is reached when 2 points like objects cannot be images as 2 distinct structures. You can see here we know that there's 2 objects, 2 points, and the distance in between is like 10 centimeters. Then we just move these 2 points closely, and at a distance of 0.1 centimeters, actually we cannot determine there are 2 points. So we can define we have the resolution of 10 centimeters by using our naked eyes. if we use microscope, we may reach more higher resolution. So maybe by using the wide field microscope, we can resolve these 2 points. But actually, during the practical experiment, we suffered the diffraction. So the light is not the light of 1 point is not 1 point. It is actually like a object with some dim rims. So you can see the resolution is just deteriorate. We have the like 10 micrometer resolutions, but actually it may be like much bigger. We only may have like 20 micrometer resolutions. And how do we stop these kind of problems? We have to choose the objective lens with high numerical values. So here we can see the NA value. This is called the numerical aperture. The numerical aperture value is defined by the angle of the light. Here you see this is the alpha angles, which pass into the objective lens. Let's see the diagram. So here is the angle we mentioned, and we call it alpha. And this one, objective, on the left side. Yeah. And this one is the low magnification lens. And on the contrary, the one on the right side is the high magnification lens. So typically, low magnification lens, they also have the low NA value. However, they have some benefits. They have much longer working distance, which means you can image much thicker samples, like maybe 200 micrometers brain slices. But if we want to image this kind of brain slices, we cannot use the objective lens, which much higher numerical values, because they have shorter working distance, and sometimes you may flush your cover slip due to this kind of limitations. And here, this one is the common air objective lens, and the signals from the samples, they just go through the cover slip and partially they reach our objective lens. However, there's still other signals. They don't reach the objective lens. So some may just go out, or they just do the internal reflections, then increase our background signals. That's why we need to use our oil lens. Oil lens means that we apply the immersion oils in between the lens and the cover slip. And the refraction index of the immersion oil is equal to the glass. Here you can see this is the reflection index. And so for glass, it's around 1.51. And for common air, the value is equals to 1. The value equals to 1. So if we use oil lens, there's no aberrations in between the samples and lens. And also, we can just collect all the lights emitted from the samples or pass through the samples. And here we have the functions to determine the resolution of our lens, and we just see the simplified one. So the resolution is proportional to the wavelength. Here, for example, for green light, the wavelength is around 550 nanometers. So if we use the air objective lens, the NA value is around 1. So 550 divided by 2 is around like 275 nanometers. This is the resolution limitations of our light microscope systems. So we just go to the real case, and we can see there are some E. coli bacteria in this image, and this is the best images we can get by using the light microscope. We can know how many of them in the field of view, but this is the resolution we can get if we want to see the details on the surface of the bacteria. Here you can see the edges, which is quite blurry, and you cannot resolve any protein complex on the surface. So let's see. Carl, maybe we just go to the optical section, right? We can pass these two sections. Sorry, I need to go out the slide. And here, sorry, we just have plenty of slides, but we have quite a few times. And here. Okay. Yep. So, okay, this is my pointer. So we just go direct to the optical sectioning method, because this is the reason why we want to use confocal microscope. For example, in this image, we have these beautiful ladies in the middle, and we also have some unwanted background informations like the guy here, and also some lecture or this kind of stuff. We only want the focus part, so just the lady and just like this. This is the ideal situations we want. Then this is the most common case when you try to do the fluorescence images or also for the bright field. And your sample, the lady, is covered by the signals from out focus plane. And maybe you already know this guy, the JYP. Okay. So this is our sample in the focal plane, but we don't want the out of focus signals. So underneath our samples or just outside our sample. So we want to try to collect only this part. And here we can see this is the conventional image taken by the wide field fluorescence microscope, and all the signals are actually composed by two sources. The one in focus and the rest is the out of focus structures. So by using confocal microscopy, we want to extract only the in focus structure. Okay. So first, we need to know how does the out of focus light come from. Here we can see this is a clear point, and this is a fluorescence point source. And in ideal light systems, this is with clear edge. However, you know, our light microscope is composed with many parts, and also our light, they go through the lens and also maybe go through like air or other mediums. So once the light passes through the medium with different refractive index, our signals, the light suffered diffractions. So here, that's why you can see there's some area disk of our 1-point light source. So this is for the XY plane. Let's go to check the XZ plane. So let's consider the Z-axis. So the signals actually deteriorate much worse if we go through the zigzag image. So this is actually not a point anymore. It's like ovate structures. So we know based on the functions that is here for z-axis, you may experience much more diffractions when you try to go focus through your samples at z-axis. And let's just dissect the signals by using the optical sectioning. So, for example, the zero position is in the middle of this image. Then we just go to other planes and take serial image. Here we take 5. Then we actually collect some out of focus structures and just listed here. For wide field microscope, actually we just collect all of these 5 layers and put them together. That's why you get the blurry image. Here, if we do the simulations of the signals which emitted from different z-axis, actually, for this plane with the highest signal intensity, this is the only plane we want to collect. We don't want signals which contribute by other layers. So to deal with this kind of problems, we want to apply the optical sectioning method. But actually, based on the series, and we can divide the method into major 3 classes or 3 groups. And the first one, we can resolve the image by using image processing, and the most famous one is called the structural illuminations. And in the middle is the one you actually very familiar with, is the confocal microscopy. And for this one, maybe you also use the multiphoton microscope. And for this group, scientists try to deal with the out of focus structures or signals by altering the light paths. We will go into detail later. So we try to depict the effect of the diffraction. So that's why we use the point spread functions. So this is the definitions by the mathematics. Then, so let's go further. So this is just the function if we try to quantify the effect of diffractions. Then, based on the computer science, if we try to collect the signals from our samples, then the sample is like how should I say? If we do the convolution of point spread function we just mentioned on the slide before, this is why we get the blurry images, because the point spread function imposes the diffraction effects onto the clear sample signals. For now, we try to just do the process from inversely. So we do the deconvolution process. This is the image we get from our maybe confocal or wide field microscopes, and then we do the deconvolution calculations. So based on your optical systems, we may design different deconvolution algorithm to cope with different situations. Then we try to retrieve the images with clear structures. And this process is called the deconvolution. And this can be applied to very simple systems, just like the wide field systems. But you can also do this kind of works on the confocal images or also the super resolution. Okay, so all these techniques, deconvolutions for deconvolution, the main limitation actually is imposed by the computation abilities of the computer, because you need lots of memories and also good graphic cards to do this kind of calculations. Then Apatone is actually another technique, and I'm afraid I have to skip these sessions. Apatone actually is just a simple gauges. Here you can see we just insert the apatone in a wide field fluorescence microscope. We can do the structural illuminations, and we can gain the images just like the confocal. Then we just jump to the confocal image here. So for let's see the image on the top. This is the one acquired by the wide field systems. You can see there's no clear edge on your samples. Then if we take the same images by using confocal microscope, then we can remove the out of focus signals and only extract the layers we want. This is why we need to use the laser light source to do the confocal microscope, because laser is with much more intensities, so it can penetrate through the samples and into more deeper parts. And also, laser light scatters less compared to LED lights. So here is our light source laser. Then it goes to the dichroic mirrors, which reflects the light to our samples. And here you can see we annotate a focal plane here. So the focal plane emits the light, the signal we want back to our detector here. However, if we don't have any filters to filter out the out of focus signals, we may just collect all the signals here. That's why we apply the pinhole here on the focal plane, just back the dichroic mirror to filter out lights. For example, for the lights from the upper layer, and also filter out the light from the lower layers, because the other layers besides the focal planes is just out of focus signals. So here, for example, the signals just come from this plane, the red one, then converge before the pinhole. Then, because the light just spin, right? It's not converged at the pinhole, so the signal are filtered out by the pinhole and only leaves the in focus signals, the green one, to go through the pinhole. So actually, we just impose lots of energies onto our sample, but we only collect a few parts of our emitted energy. So let's see these animations. So these two gray rectangles are like pinhole. So they only leaves the sharpest peak, and this is the in focus signals we want. So we only collect this part of signals by using this one called PMT, the photon multiplier. And if we try to compare the wide field system and the confocal systems, let's see. So for wide field, it's just like using your phone, like iPhone. Just one click with just one shutter, you can get your images. However, you actually collect a volume. This one, a volume of signals. So the signal is composed with in focus and also out of focus one. But for confocal, this one is like a printer. So it's do the point scanning, and which takes much longer time compared to wide field systems. However, we can extract the in focus signals by using the confocal systems. Then we do the Z-stack imaging. So we take multiple images at the Z-stack, but every stack is with in focus signals. Then we can project or to do the 3D reconstruction to gain the whole data set without out of focus structure. And here we can show some applications. For example, we can do the live images. Here we can see the microtubules, which is labeled green, and also the nucleus, which labeled red. And you can see the resolution is pretty high. And also, this one is the Drosophila brain. And you know, the Drosophila brain is covered with the outer layer. It is mainly consists of cuticles, and cuticles is actually like hinders the light pass through the samples. But by using the confocal, we can just simply use the laser light to go through the cuticle layers, and then we extract the in focus structures here and do the Z-stack images to reconstruct the region of interest we want. If we have this is the retina tissue of mouse eyes. So this kind of samples, they cannot be images with much higher intensities. So by using the confocal systems, for example, the LSM 980, we can do the tile scan, which means we collect multiple images as XY axis, and then we do the Z-stack images. We also collect the multiple Z-stack images, then we reconstruct the whole signals into the 3D data set. Actually, you can hardly see there's any aberrations. The whole data set is quite impressive. If we try to cope with much larger tissues, we use the clearing techniques. So first, for this is the mouse brain, and this part is in the cortex, and the thickness is around 80 micrometer thick, and we use the inverted confocal microscope to take this kind of large data set. I think this is around like 100 gigabytes for one channel. So this kind of data set, you can see the neurons. So from the outer layers of the cortex to the inner side, and all the structures are documented quite finely. So from the neuron and to the dendrites. We mentioned the resolution limitation is around like 200 to 300 nanometers, depends on your wavelength. If we use like the blue light or the purple light, we may have higher resolution, but the value is just quite large for researchers. We want to have super resolutions, so we can observe the two layers of mitochondria, or we want to see the organelle, subcellular organelles much more clearly. That's why we apply several other techniques, and the one is called Eriscan. For conventional photomultiplier detector, and this is the image on the left-hand side. This one is acquired by the conventional detector PMT. So, and the image on the right is acquired by the newer type PMT. It's called the Eriscan. So let's compare the details by enlarge the image. Then we can see. So by using the conventional techniques, we can hardly distinguish how many protein structures is on the so it's called telomeres, right? Yeah. So we go further by using the Eriscan. Here we have higher resolution, so now we can visualize how many telomeres on the end of the chromosome. And what is Eriscan? So we just see another case. So for the microtubules or other subcellular structures, we want to see them much more clearly. But all the limitations is actually caused by the diffraction. So like we'll just go back to the point spread function here. So this peak is the signal we want. So that's why we usually say the image parameters is like 1 area unit, because 1 area unit provides enough signals and the signals we want. However, if we want to increase our resolution, then we need to close our pinhole to less than 1 area unit. Let's just go to check. Sorry. Okay. So based on the previous work, so the engineers in our Germany headquarters, they do this kind of test. So if we want to reach much more higher resolution by using the conventional photomultiplier detectors, we actually lose a lot of signals we want, and it may reach about like 95% signals. So even you can image it with higher resolution, but you can only acquire only 5% of your original signals. So that's nonsense. We want to have all the signals. So that's why Zeiss provide the Eriscan solutions to deal with this kind of situations. If we have limitations of one detector, how about we just put 32 detectors together we do the array detector. And each detector can have much more smaller area units, which means with higher resolution. And also by doing the array detectors, we can actually have the resolution at such small 0.2 area units. But the capacity of collecting signals is at 1.25 area units. So we have higher saturation, but we also have much more brighter signals. Here you can see this is the array detectors composed of 32 GASP. This is the GASP PMP. And so the principle is actually we use the 0.2 area units PMP to collect the most resolved signals here. And here we see the animations. This is the conventional confocal microscopy. So the blue one is our laser beam, and the green one is our sample. Then let's go scan. So you saw the signals actually blurs. Then this is the area scan. Oh, sorry, this is not area scan. This is the confocal with much smaller pinhole. It's like 0.2 area units. So with such small pinhole, we lost a lot of energies here. And this is the area scan array detectors. So by using the array detector, we actually collect all the signals, but at higher resolution. Let's compare the results. So here, the image on the left is the conventional confocal image, and we can compare the images by this one. So we use area scan detector first. We detect the signals. So this one, but it's like we want to see an object with one detector, but now we use 32 detectors. Try to document the signal from only one object, but we need to reassign the pixels because each detector is placed at different locations, right? So we need to reassign the pixels, try to put them together and reconstruct the higher images with higher resolution. So it's just like this one. Okay. Oops. So the slides, the slides are stuck, right? I cannot move the slide anymore. So maybe due to the connection problems. So let's try again. Okay. So we can compare the time series image data set. The one on the upper side is taken by the confocal microscope, and the one on the bottom is taken by the area scan image. So we can clearly see the improvement in resolution. Not only for the 2D dimensions, and we can only acquire much higher resolution also in the 3D data set. So here we can see at the axis, and the details are all well documented. And here's another case. So if anyone is doing the Drosophila research, you may be quite impressed because I have heard that if you try to, oops, if you try to image the bush pilot, these kind of structures, and it's very challenging if you want to take the super resolution image. And also for the live cell images, every scan can also take the time series and without crunching the cells. Let's see, oops. So here's the animations of the time series data sets. We can see the chromosome and the microtubules, right? I just wait. Is it microtubules or a tubulin? So the green one is tubulin, labeled by GFP. Okay, so now Zeiss try to develop much the newer techniques about the super resolution microscopy. That's why we provide the ELIRA 7 and with the algorithm, the newer algorithm called the SIM square. So here the structural illuminations, and for every scan can raise our resolutions from 200 nanometers to around 120 nanometers. However, if we want to just to move forward, less than 100 nanometers at resolution, ELIRA 7 can reach the resolution around 60 nanometers. So, which means that you can resolve the subcellular structures like the mitochondria or the ER, and maybe mitochondria labeled properly. You can just image these kind of samples, even in time series, because instead of using the photomultiplier detector, ELIRA 7, we use the CMOS camera. So that's why we can take 255 frames in merely 1 second. So every fast event of life cell can be documented by using the ELIRA 7, and you can also have very high resolutions, no compromise. Sorry, just pass this slide. So why do we need to use the structural illuminations for the ELIRA 7? So for our routine microscopy, we have the wide field microscope, just like a common fluorescence microscope, but we can only image the samples down to like the individual cells, but we can hardly see any organelles inside. Okay, let's try it. We apply the confocal microscope. Some organelles may be visualized, but we cannot just visualize all kinds of organelles. So we need to raise our resolution. So here we come other techniques. So we have the classic structural illuminations, and also the stimulated. Sorry, I forgot the whole name. So this is also another super resolution technique, and this technique is right now owned by the Leica. So if you we want to have higher resolution, super resolution, but we also want to image both the fixed cells, fixed samples, and also the live samples. So we want to image all kinds of sample types, right? So we don't want to use very expensive machines. It costs like how much? Like 1,000, 1 million, maybe 1 million, right? 1 million US dollar. So we invest 1 million US dollars to only take the fixed samples. It's just too over. We also need to cover the live cells. So that's why we have this part. We have ELIRA 7. So ELIRA 7 systems can actually cover from the tissue type samples and also to the live cell images and have the higher resolution, can document the subcellular structures. And also it has much higher image speed. So compared to like the single molecular techniques, like POM. So if you want to take this kind of techniques by using ELIRA 7, we have the camera instead of the photon multiplier. You can just document at very high frame speed. And by applying the sim square algorithm, we further improve the resolution. So here, this is the time series data set, and so microtubule is labeled as green, and we can also see the ER endoplasmatic reticulum is labeled as magenta, and we just enlarge. So there's no detail image. So we still have time or not?
It'll be over that time.
Over time. Okay, then we just see the animations of this. So how about the principle of the ELIRA 7? This is the conventional design. So we apply the line grid to impose on the sample. Then we have the coarse frequency speed. It's called just like Moore fringes. Then we document the Moore fringes, means the coarse frequency speed, the thicker line here. You see the green one. And we also know the frequency about provided by the grid here. The green one is our samples, and we can recalculate the frequency of our sample based on the grid and also the image frequency speed. And the new design, we apply the grid with hexagonal dots. So we don't need to rotate the grid. We just only to move up or move aside the grid, so which provides much faster image speed. So let's compare the classic sim and also the latest sim. So for the conventional one, the grid have to do the rotations. So each rotations just costs another times for your imaging process. So that's why we apply the lattice grid, just like this one, the hexagonal type. So we only need to move the grid vertically and horizontally. And further, the lattice type sim also enhance the resolutions. We just go to the details. The most interesting part is this one. So if we try to resolve the really fine structures of the protein complex between the how should I say, the synapton, right? The two synaptons. And here, this is the images acquired by the new sim square techniques. And we can actually see there's two blue chromosomes and the red and the yellow internal structures. we can visualize the details. You can see the resolution can reach about 50 nanometers. So even the scale bar at 1 micrometer is much larger than the actual resolution. So if you try to acquire much higher super resolution images, I would suggest you to try the ELIRA 7 microscope. You can just experience the power of the machine. So I think I can finish the stations here, right? So any problems or anything you want to ask? No? No? Okay. Anyway, if you have any problems, you can just contact the technicians for any support. Thank you.